example choice, let us say we choose n equal to 8, right, and recall that m ln n is about 20, must be chosen to be about 24, correct, all right, and if ln n is 8, m must be approximately 24 by ln n, which is approximately 11.5, something like that. So, we can go and find that m needed to get. All right. Okay. So therefore, the idea therefore now is that let us say we have two voltage sources VD1 and VDN. Can we just go back and think about the various circuits we have seen in the past and generate a voltage VD1 times m plus 1 minus m into VDN? Yes? Okay. So how will we get an output which is m plus 1 times VD1 minus m times VDN? Okay, if you use a non-inverting amplifier, let me okay, the suggestion is use a non-inverting amplifier, okay. Yes? Okay, so basically we put R here, we put so if this was VD1, we put say R and MR, okay. So, this will give us m plus 1 times VD1, okay. How do we get minus m times VDN? Connect VDN at? Very good. So, basically if we put VDN here, then this will be minus m times VDN, very good. All right. So, now the question is now we need to put VDN and VD1, we need to put diodes to generate that VDN and VD1. So, basically to get VDN we simply put a diode of size n, correct. So, what will be the current flowing through this diode? This is VDN. What will be the current flowing through that diode? VD1 minus VDN by R. All right. Okay. This is that. Now, we need to generate VD1. How will we generate VD1? You put a diode, okay, and but I mean to generate VD1 some current must flow through the diode, isn't it? And for the for VD1 minus VDN to be PTAT, what current must flow through VD1? The same current I must flow through this diode. Correct? Okay, can you stare at the picture and tell me if there is something simple that we can do to ensure that? What is the current through MR? What is the current through this current I in the in the N size diode? Where does it flow? Through MR. Okay. All right. Now we want the same current I to flow through the single diode. So what should we do? What should we do? What do you do? What do you think we could do to make that happen? Keep why? Keep M times R resistor between
the VD1 and the
output terminal of the op amp, right. So, why? Because the current I is basically this voltage minus this voltage by MR, right. So, and this voltage is the same as that voltage because of virtual short. Okay. So, so what should we do to make sure that a current, the same current I flows through the diode of size 1? We must put the same resistance between so this must also be MR. Is that clear? Okay. So, this current is also going to be I, and therefore, VD1 minus VDN is going to be PTAT. Okay. So, if the circuit is redrawn in a different way, this is VD1, this is VDN, this is basically M times VD1 or VD1 sorry, plus m times VD1 minus VDN. Is that clear? Okay. So, what is the current that flows? Okay, let us assume that you have never seen this circuit in your life before. So, how will you analyze it? Analyzing is easy. What I mean, the two inputs of the op amp are identical. So, if these two voltages are identical, then these two currents are identical, correct. So, the currents in the branch on the left and the branch on the right are identical. So, this is VD1, what comment can you make about that voltage? VD1. So, what is I? I is nothing but VD1 minus VDN by R. And what is VD1 minus VDN? Phi t ln n by R. Is that clear? And therefore, what is Vref by analysis is nothing but VD1 plus I times MR, that is basically this voltage plus the voltage drop across MR. So, that is basically VD1 plus phi t ln n times n. Okay. So, the current, I mean the current as you can see is the PTAT current, right, because it depends only on absolute temperature. Is that clear? So, as I said, a common choice. So, of course, now I mean if you go and buy a reference off the shelf, basically all this stuff is inside that IC. Okay. But so, it is not as if you are going to be building it on a breadboard this way, right. But this is a useful illustration of seeing an op amp in a negative feedback loop, where if now you can look at it, there are a lot of elements here which are non-linear, okay, and the output of the op amp does something useful. And as I said, this is called the band gap voltage reference, and a common choice for n, remember that we said n is 8, and the reason for making n 8 is the following. So, basically the one diode is chosen like this, and the other 8 are placed around the one diode in this way. Okay. and the reason is, can somebody think of why the diodes are placed this way? I mean, looking down from the top of an IC, this is how the diodes would look, and that is the boundary of the, I mean, each square I have drawn is basically p doped semiconductor sitting on, say, an n doped substrate, right. So, why do you think the diodes are the n diodes are kept? Why is n equal to 8? Why do you think it is a good choice? I mean, okay, I mean, if what if we chose 4 diodes? I mean, why not choose something like this?
The diode one has the diodes on right and left side, but there is no diode on top and bottom.
Okay. I mean, basically the reason is the following, that if there is a temperature gradient in any direction here, right, the average temperature of all of these 8 diodes is going, because this is the centroid of all of them, the average temperature of these 8 diodes is going to be the same as the temperature of the diode in the middle, right. Otherwise, what will happen if it is not symmetric with respect to the centroids of the n diodes are not the same as the centroid of the one diode, then if there is a temperature gradient, then some diodes will be at some temperature. I mean, the VT ln n is only possible when the diodes are all at the same temperature, right. So, n is a common choice, and so is 17, because I mean, so is 15, because then you can put a 4 by 4 array, not 15. You need to put 5. I mean, 24 is again another number, right, but n equal to 8 is a common choice, right. And then you need m equal to roughly about 11 and a half or 12, right. So that you get 24 VT, and okay. So this is this is an example of using an op amp in a feedback network where elements are nonlinear, where the output of the op amp does something useful.